In this lesson, we build intuition for the interplay between spontaneous curvature and force-induced tubulation in membranes. Our goal is to see how tube width is set by a composite curvature, and how force and curvature either work together or against each other. Let's sketch a giant unilamellar vesicle, a GUV, with a cylindrical tube. We will use a two-dimensional cross-section. The sphere segment is large, and the tube can protrude outward or inward. We adopt a sign convention. Positive force points outward toward the exterior solution. Positive spontaneous curvature means the membrane prefers to bulge outward. We define the composite curvature, m sub com, as m plus f over 4 pi kappa. This composite curvature is the key quantity controlling tube size. When m and f have the same sign, they reinforce each other, synergy. When their signs are opposite, they partially cancel, antagonism. In the regime where the composite curvature in magnitude is much larger than the inverse vesicle radius, the tube radius is set by the composite curvature. Specifically, our sub cy is approximately 1 over 2 times the magnitude of m sub com. That means tube diameter scales, like 1 over the magnitude of m plus f over 4 pi kappa. The tube mean curvature has a small correction from the finite vesicle size. M sub cy is approximately m sub com minus 1 over 4, our sub sp, valid for large vesicle radius. Out tubes correspond to positive composite curvature. In tubes correspond to negative composite curvature. At mechanical equilibrium with a large spherical mother vesicle, the composite curvature satisfies approximately m sub com is plus or minus the square root of sigma hat over 2 kappa minus 1 over 4 are sub sp, with plus for out tubes and minus for in tubes. The total membrane tension, sigma hat, is the sum of the mechanical tension, capital sigma, and the spontaneous tension, sigma, which equals 2 kappa m squared. A neat experimental strategy is to pull both an out tube and an in tube from the same aspirated vesicle using an optical trap. Let F sub x be the outward force, and F sub n be the inward force, both measured at the same aspiration pressure. Then adding the two relations yields a simple estimate for the spontaneous curvature m. It reads, m is approximately minus F sub x plus F sub n over 8 pi kappa minus 1 over 4 r sub sp. For symmetric bilayers, m equals 0, and this implies F sub n equals negative F sub x. In some experiments, an aspiration tension is computed from the micropipette suction and geometry, but the total membrane tension, sigma hat, differs from this aspiration tension by an additional term that depends on spontaneous curvature. The aspiration tension is sigma asp equals pressure outside minus pressure in the pipette times pipette radius over 2 times 1 minus pipette radius over vesicle radius. The more general relation is sigma hat equals sigma asp plus delta sigma hat, where delta sigma hat equals 2 kappa m times the quantity 1 over pipette radius plus 1 over vesicle radius. For example, take kappa equals 10 to the minus 19 joules, pipette radius 3 microns, vesicle radius 6 microns, and m equals tilde m per micron. Then delta sigma hat is about 0.1 times tilde m micronewtons per meter, which is already about 1 micronewton per meter for tilde m equals 10. At very small aspiration pressures, this extra term is not negligible. All these simple tube expressions require that the magnitude of m sub com is much larger than 1 over r sub sp. This fails in two situations. First, when both the spontaneous curvature and the scaled force are too small compared to 1 over r sub sp, no tubes form. Second, when m and f over 4 pi kappa nearly cancel, tubes can still exist, but their curvature depends strongly on vesicle size. In that cancellation regime, theory predicts the tube mean curvature scales like plus or minus the quantity, absolute m times m sub sp squared over 4 to the 1/3. To close, watch how the tube thickens when the composite curvature approaches 0 and thins when the composite curvature grows in magnitude. First synergy, then antagonism. The big idea is that tube width is controlled by the combined action of spontaneous curvature and pulling force through the composite curvature. Summary: composite curvature m plus f over 4 pi kappa controls tube size. Out tubes for positive composite curvature, In tubes for negative, finite vesicle size adds a small curvature offset. Total tension is sigma hat, not simply aspiration tension. An M-dependent term can matter. Optical trap, pulling in and out, provides a tension-independent estimate of spontaneous curvature.